Hello everyone, welcome back to ptet.chemistry channel. So this is a series of topical MCQs on chemical structure and bonding. So I've had to change these, I figured that it's better to just actually change what I had previously done incorrectly. And thanks to one of the viewers, one of you guys out there, who actually spotted my mistake and therefore let me know. So rather than introducing corrections image, I figured that since I have the chance to actually re-edit the video, I might as well just do it again. So this is actually a re-edited question 21 based on the comments by one of the viewers about a mistake that I made previously. So what mistake had I made? So it's asking here, these are chloride compounds. These are chlorides of third period. So period 3 chloride is actually part of your AS general periodicity case study. You want to be described as ionic with some covalent character. So you want to be described as ionic and some covalent character. My previous mistake was to choose AlCO3 straight away, but that is actually wrong, because if you think about how they usually like to ask you, what kind of structure do you have? Well, for NaCl, you have giant ionic structure. MgCl2 is also giant ionic structure. But for AlCO3, we know that it's already simple covalent or simple molecular structure, as the AlCO3 easily sublimes to the Al2Cl6 dimer in the gaseous phase. SiCl4 is also simple molecular. And the fact that they exist as one single molecule, you can draw them as this kind of display diagram, but you can't do similar things for giant ionic structure because these are lattice. They are not existing as single molecule, whereas simple molecular structure that exists as discrete, single, discrete, meaning individual covalent molecules. That's why they can have molecular formula, which is the actual number of atoms in one single molecule. You can't ever have molecular formula when you talk about lattice structure, which is continuous network. So in terms of describing as ionic, therefore, we can cross out C and D because C and D are never ionic to begin with. And then some covalent character. We know that you have Mg2 plus and Na plus, bigger charge cations. So we say higher density, higher charge density equal to charge over volume. So Fajian's rules is basically quite a hand-waving way set of rules talking about the degree of covalence in compounds, in ionic compounds. So the bigger charge cation, the smaller size cation is going to have a greater degree of covalency, because smaller cation, bigger charge cations, they are more polarizing on the anion. So B is actually the correct answer, and not C, which I previously stated because, I missed out that particular fact there. Alright, so yeah. In this next question, you have this lycra, which is a polymer, is a polyurethane, and you are made up from two monomers. And this is one of the monomers shown here. They just want you to work out the OCN bond angle. So the OCN bond angle is here. Because they are looking for OCN, we just need to look at the central carbon atom, the central atom there. The central atom there is this and this. Looking at the carbon central atom, so about the central carbon atom, we count the number of sigma bond. So this carbon atom has a double bond, but that double bond is 1 sigma and 1 pi. That double bond is 1 sigma and 1 pi. We just need to look at the sigma. So around that carbon central atom, you have 2 sigma. Therefore, we have 2 bond pair of electrons, okay? And then the carbon has used all the 4 outer shell electrons for bonding because it has formed 4 covalent bonds altogether. So it's used all 4 of its outer shell electrons for bonding. You have 0 lone pair of electrons. The 2 bond pair of electrons with no lone pair of electrons, they will repel equally. And as part of it, you will get linear 180 degree, just like in CO2, which is part of your case study. In VSEPR, valence shell electron pair repulsion theory, where you need to state the number of bond pair, lone pair, talk about repulsion before you talk about shape and bond angle, rather than something and then straight away the shape. No, you need to talk about valence shell electron pair repulsion theory. So that's just 180 degree over there. This next question, it's saying that you have a triethylamine with boron trifluoride. So this one has got a lone pair. The boron there has got an empty orbital. So this is a variation of the standard classic, which is H3N plus BH3. I mean, they are similar. I mean, the same concept applies here because the boron there is a group 13. So group 13 element has 3 outer shell electrons. It's used all of them for bonding. But then it's also got another empty 2p orbital on the boron. So these are empty. And what happens for the NH3 is that your NH3 has a lone pair of electrons. And the lone pair of electrons can fill in the empty orbitals. And what happens then is you would form a dative covalent bond where that lone pair donates to the boron empty orbitals, and instead of being trigonal planar, which it was previously, now it becomes tetrahedral. This is a nitrogen with 4 bonds, this is a boron with 4 bonds. It has gained the electrons from nitrogen, the nitrogen has lost electrons to the boron. So I've just shown you for example with NH3 and BH3. So instead now, what we have instead of H, and H, we have Me, and Me, which is CH3. Instead of BH3, we have BF, F, and F. They are the same thing. They are the same deal. That's why chemistry seems difficult for a lot of students, because they thought they only need to know one example. They can't relate it to whatever they see in a new context. In a new context, you have a change of geometry. So this is a 107 or 107.5 degree because you got a 3 bond pair and 1 lone pair. So VSEPR says it's going to be trigonal pyramidal 107 degree, which is your case study. This is a 3 bond pair because 3 sigma bond with no lone pair because boron is from group 13, uses all the outer shell electrons for bonding, trigonal planar 120 degree. Now the nitrogen has 4 sigma bond and 0 lone pair. The boron there also has 4 bond pair because of the 4 sigma bond, including the newly formed dative covalent bond. So 4 sigma bond, 4 bond pairs, 0 lone pair, both are tetrahedral, which means both become 109 degree. And if both become 109 degree, it's no longer trigonal planar, it's no longer trigonal pyramidal. So we need to think about the geometry of the final product, yeah? But looking at this, you can tell this is wrong because BF3 is trigonal planar, as I mentioned. So that geometry of BF3 is already wrong, and BF3 is your case study as part of the shape of molecule. And of course, as I mentioned, when the nitrogen dative bond to the empty orbital of the boron, then the boron will no longer be the boron will no longer be trigonal planar. The nitrogen there will no longer be trigonal pyramidal. Instead, the nitrogen will become like tetrahedral, and the boron there will become tetrahedral. So C is the correct option and not A, because of the geometry presented by the BF3 there is incorrect to show us the tetrahedral geometry as a result of this formation of dative covalent bond. In this next question, this is about hydrogen peroxide. Well, it's about peroxide, it's not about hydrogen peroxide. But when you have a group 2 forming a compound, you have a Ba2+, okay? Therefore, that whole thing is a 2-. When you think about hydrogen peroxide is H2O2, and you know from GCSE or O-level, oxygen always has an oxidation state of -2 in a compound, except in molecular oxygen when you have 0 oxidation state, and also except in peroxide, such as this peroxide, when the oxygen is -1 oxidation state, because that oxygen is bonded to itself. It's only bonded to one other thing where it has different electronegativity too. When you have O2-, you can think about a minus there and a minus there, because think about losing the H+. H+ has no electrons, so it gives the electrons to the oxygen, so it's a minus. H+ has no electrons, it gives the electrons, which impart the negative charge on the oxygen. So what happened then is, when we think about the peroxide ion, this is the peroxide ion, okay? the barium has lost the electrons, okay? So we are not looking for B because there is no electron from the barium. The peroxide ion is a O2 2-, so it's not just one single oxygen, all right? And we are looking for one electron from each of the barium, okay? Just like that, but there's covalent. We are looking at ionic, okay? So the barium has donated one electrons to each of the oxygen. So we are looking at D because the negative charge is on each of the oxygen rather than concentrated on only one of the atom. And this one has incomplete octet configuration, whereas we're looking at each of the oxygen gaining one electrons and therefore gaining the 8 electrons in the outer shell, completing the octet electronic configuration. This is the last question of this 5-question series. So in line with the first question of this 5-question series, there was a question about the formation of covalent compounds, meaning to say ionic compound with a slight covalent character. We talked earlier about Fajian's rules. We talked about Fajian's rule basically saying that the covalent tendency to form covalent compounds or tendency to show or exhibit covalent characters come as a result of large anion and also highly charged anion. But that is not being asked here because this is all metals. The metals form the cations, so we are talking on the cation character instead of the anion character. So we say those anions are polarizable, more polarizable. In terms of the cation, you want small cation. You want highly charged cation because small and highly charged cation will give you more polarizing cation. So if you have more polarizing cations, more polarizable anion, you have greater covalent character. When you are ionic, you have greater covalent character. When you have highly charged cation and also small cation, and that's the case with aluminium, as I shown earlier, I think in the first question of this 5-question series. In AlCO3, you have Al3+, which is very highly charged cation and also very small cation. As you know, ionic radius of Al3+ is smaller than Mg2+, is smaller than Na+. Ionic radius was covered in the last topic under atomic structure and will be revisited as part of general periodicity in topic 9.1. So this is the end of this 5-question series. If you find this tutorial helpful, do subscribe to the channel, share them widely with friends, class group chat, and teachers, and etc. Okay, so I'll see you in the next video. Thank you for watching.